Hello there and welcome to this Carlam Cymru session for GCSE Digital Technology. Now in these sessions we're going to be preparing for the Unit 1 exam, and over the next 3 sessions we're going to look at 3 of the maybe most common topics that are going to pop up in the exam whenever you're watching these videos. So in this session, as you can see on your screen right now, session number 1, we're going to be looking at topic 1.1, which is analog data and digital data. And then in our next session, we'll be looking at topic 1.2, which is storing data digitally. And then finally, we'll have a live session, session 3, which will be concentrating on topic 3.1, which is communication methods. But also, if you've got any questions that have popped up when you've been revising, maybe for the first 2 topics or any other topics, nothing too difficult, mind, then you're welcome to pop along to the live session and ask your questions, and I'll try and help you out on the live session. Obviously, the live session will also be recorded, so if you miss it, you'll be able to catch up with that just like you're watching this one now. So anyway, on to tonight's session, which is session 1, analog data and digital data. Okay then, so what then is analog data? Now we're studying digital technology GCSE, so obviously the word digital is in there. So digital means the way the computers deal with data. So what's analog? Well, analog data is basically how the real world works. Outside of computers, analog data is sound waves that you're hearing right now, grooves on a vinyl record, paint on a canvas. It's everything around us. And analog data is data that is physically represented. So that means that sound waves, although we can't see them, they are physically waves. They are physical waves that are traveling through the air from the sound source to our ears so that we can hear it. So analog data, it varies continuously. So what that means is that with analog data, if you zoom in on it, if you zoom in on a little section of analog data, it doesn't matter how far you zoom in, you'll always see new information all of the time. It never kind of hits a brick wall and where it says, right, that's it, that's the end of the data, there's no more now, you've zoomed in too far, or you've zoomed in as far as possible. With analog data, it doesn't matter how close we get into it, it varies continuously. It's always something new to see by looking at it closer. So we've got some examples here of analog data and devices. So you can see there in the top left-hand image, it's a classic analog radio, like an FM radio. Now, I'm sure you've come across these. I've got one in the car. When you're listening to the radio, sometimes you lose a bit of signal and you'll hear some static, some interference in there. Kind of sounds like rain, sounds like crackling static. So that's an analog form of data that we're listening to over the radio. A really good example, and an example that WJC really like, is the grooves on a vinyl record, so on an LP. Now, actually, in the knowledge organizer, which I've used for the text on the screen right now, you can see there the last bullet point but 1. They're actually using the word lines on a vinyl record, or gaps on a vinyl record. Now, I don't particularly like either of those words, lines or gaps, because what they are grooves. So with a vinyl record, it's just a plastic disc, and the grooves have been cut into the disc or pressed into the disc. And those grooves, if you zoom in on them far enough, you can actually see the sound waves of whatever's been recorded. And then to play that back, then obviously your record player, as you can see in the image on the top right there, has got a needle, and that needle just follows the grooves and plays back whatever the grooves have recorded. An electric guitar. Now then, don't be fooled, don't be tricked into thinking that anything electric has to be digital. Our first 3 examples there are all use electricity, the radio, the record player and an electric guitar, but they're all analog because nothing's been put through a computer here at all. Okay, with an electric guitar, there's no computer involved. The strings are like a normal acoustic guitar, but then you've got pickups, which are kind of magnetic coils, which then transfer the sound waves from the strings as magnetic waves down the cable to the speaker or the amplifier, where it's reproduced at a louder volume. Finally, there in the bottom right, we've got film from a film camera. Okay, and your normal film camera, which takes a roll of film. So that, again, is analog data, and the camera is an analog device. I'm sure you've seen, old movies where somebody maybe zooms in or blows up a photograph taken on a film camera, and it never pixelates. Now, I'm sure you know what pixelation is, where you see the squares that make up a digital image. With an analog image taken on a roll of film, you never get that. When you can zoom in as much as you like. Now, you will see static, you'll see noise, you'll see kind of graininess, but it will show you everything that's there, and you can keep zooming in, and zooming in. Okay, so what then is digital data? Well, for us to use data on a computer, it has to be digital, because our computers can't store sound waves. Yeah, we can't catch sound waves in a jar, put a lid on the top, and put it in our computer somehow. And we can't put the Mona Lisa into a computer, canvas and paint and all. Okay, so in order for us to store information on a computer, it has to be digital. So what does that mean? Well, digital data, when it boils down to it, has to be converted into numbers, and numbers at the end of the process have to be converted into binary. Now, binary is a form of storing numbers which only uses the numbers 1 or 0, as you can see there in the first sentence. So digital data is a combination of numbers 1 or 0. It has to come back down to that. Above that, kind of before it's converted into ones and zeros, we have to convert it into numbers. Now, what's another word for numbers? Digits. Digits, digital. So the word digital comes from the fact that anything that we store on a computer has to be at some form converted or turned into numbers. And we'll be looking at how that's possible in the next few slides. So examples of digital devices, we've got a tablet there on the top left. Remember in the exam, they don't want to see any brand names, so you wouldn't want to write the word iPad, okay? You probably won't get the mark if you write iPad, iPhone, Apple Watch, any of those things, no brand names, okay? So an iPad is a tablet computer, or a tablet. So tablet, we've got digital cameras on the top right, and then we've got a smartwatch on the bottom left, and we can see there in the final image there, bottom right, just it's kind of a representation of how data is stored digitally, where it's all converted into ones and zeros at the end of the day. Okay, let's move ahead then. So we've got a question. Here's an example question. Now then, when you turn a page or click to turn the page, I'm pretty sure that your first page of questions will have this topic. I reckon, I could be wrong, and now I'm on record as saying it, but I reckon that this topic, 1.1, analog data and digital data, will be the first question on pretty much every paper we see for the next however many years digital technology is going to run, okay? And if you see a tick box grid like this, it should be full marks in the bag, okay? You should be able to look at this, use your common sense, use your revision, and get all of the marks. So tick the correct boxes to show whether the following devices are analog or digital. So we've got 3 devices there, and we've discussed them all already. An electric guitar, a tablet, and a smartwatch. So an electric guitar is what kind of device, guys? Is it analog or digital? If you said analog, that's correct. An electric guitar is an analog device. And then a tablet and a smartwatch, both of those are digital devices. So the correct answers there would be analog, digital, digital. And that would be 3 marks in the bag, 3 out of 80, okay? It's only 80 marks, and if you get 3 of them for just ticking boxes, it's a good start. Okay, the next questions, we got 2 1-mark questions here, which ask kind of the opposite ends of what we've just been looking at. The first one, B1, state what's meant by analog data. Now, what do WJC want you to say there? Well, I've given you the answer. It's highlighted on our very first slide. Analog data is data that is physically represented. Now, just that first sentence will get you the mark. Or you could just give them the second sentence. That would also give you the mark. Or, if you're confident and you've remembered it well, you could give them both sentences and that'll definitely get you the mark. But analog data is data that is physically represented. Okay, and I really like this second sentence as well, that analog data varies continuously because digital data can't. Okay, the next question then is state what is meant by digital data. Well, again, if we go to the digital data slide, either one of those 2 highlighted sentences will get you the mark. Digital data is a combination of numbers 1 or 0. Computers use digital data to represent data. Okay. So, hopefully you can see that, these questions on this topic, are okay so far. So what about graphics then? How are we going to store a picture on a computer? How can we turn a photograph, or how can we turn a painting or an image or a logo into numbers? How can we turn graphics that we see into numbers? Well, basically what has to happen is that we have to turn that graphic into a grid. We cut it down into a grid, into squares. And those little squares are called pixels. And you can see the highlighted sentence there that says the dots are called pixels. Now, I don't really like the word dots because dots for me are round. So pixels are square. So for me, I'd rather call pixels small squares rather than dots. Okay. So if we cut any image up into little squares, we can number them. So here we go. We can start turning the image into numbers. And what do we need to store for each square, for each pixel? Well, the information we need to store for each pixel is just what color is it? And that's it. Okay? So if you look at the smiley face on the right-hand side in the green box there, you can see that this shows us how an image can be stored at the simplest level. Somebody has drawn a picture of a smiley face. So we've got 2 eyes, a nose, and a smiley mouth there. Okay? Now, this image only uses 2 colors. I can imagine that it was maybe a white piece of paper and somebody used a black pen. So each pixel is either going to be white or black. So in that case, we can use 1 bit of our storage. So bits are what we call the tiny little pieces of storage in our computer's memory or in our digital device's memory. So and a bit can only be 1 or 0, as we've discussed. So we can decide what 1 and 0 means. So we can just say, okay, for this picture, we're going to break it into squares, and then we're going to store the color of each square. And each square is either white or black. So let's call white 0, because it's kind of empty, and black is 1. Okay, so white is 0, black is 1. So you can see there, the first row across the top of that smiley face, we've got a row of all white squares. And they can all be stored on 1, 2, 3, 4, 5, 6, 7 bits across. And you can see they've all just been stored as 0, 0, 0, 0, 0, 0, 0, because they're all white. The next row then we can store, well, we've got 2 black pixels there for the eyes. So we'd store that second row as 0, 1, 0, 0, 0, 1, 0. Okay, so I'm sure you get it. Now, obviously, what do we do then if we need to store more than just two different colors? Because not many images use two colors. Even black and white images have shades of gray in between. So you wouldn't be able to store a black and white image that's got gray in it just using 1 or 0. So we need to use more bits per pixel to store more colors. Now, one of these kind of color palettes that's used a lot, especially on the internet, is called 8-bit color. Now, using 8 bits, so 8 little switches that are either 1 or 0 on your computer, you can actually have 256 different pieces of information. We can store with just 8 bits any number from 0 to 256. Okay? Now, if we give each color a number, so as you can see there in the left-hand side square, that's an example of a 256 color palette, an 8-bit color palette. So we would just go along and number all of those. So that in the top left-hand corner, it's black. So black would be 1. Then you got that really dark grey. That would be color number 2. The kind of little bit lighter again, grey would be color number 3. All the way to that weird kind of yellowy mustard color right in the bottom right-hand corner. That would be color number 256. So now you could use any one of those 256 colors. And you're going to store the number of that color for each pixel in your photograph. Now, bear in mind, maybe you know how many pixels. What is the resolution of your of the phone, of your camera on your phone? I think mine is about 12 megapixels. So that means that when I take a photo with my phone, it actually cuts up the picture that the lens is seeing, that my camera lens is seeing. It actually slices it up into a grid of 12 million pixels, so 12 million little squares. And for every square, it's going to make a note of what color it is. Now, this example here is 8-bit color, where there's only 256 colors. Okay, but on a photograph, you need way more colors than that. Otherwise, you get this weird kind of, if there's a gradient of light, you get these weird kind of bands of light. And I'm sure you've seen that, bands of color. So you then need to maybe use 16-bit color, which gives you something like 65,000 different shades of color. Or if you go to 24-bit color, you actually have millions of different colors. Okay? So you can see there the e-sgol logo. When I zoom in on it, okay, it's a digital image. When I zoom in on that digital image, it doesn't vary continuously. I can't keep zooming in because what happens is at some point I will end up with just one big colored square filling my screen. And you can see the kind of edges of the squares there on the letters. If you look at the letter E, you can see it's got that kind of staircase going up. It's pixelated, we call it. So that shows us that with digital data, you do hit a wall. You do hit a brick wall at the end. If you keep zooming in, keep zooming in, keep zooming in, there'll be a point where there is no more information. Okay, that's the flip side. Remember with analog, I can keep zooming in, keep zooming in, keep zooming in, and it'll vary continuously. It'll never reach the end of the information that's been stored. All right, let's move ahead. Sound. Now, WJC really like talking about sound. So when you get questions, I always recommend that you think about sound first. If it's talking about digital data, storing digital data, I kind of get the feeling that they write those questions with sound in mind, unless it obviously says something else. About, if it says graphics, then it's about graphics. But if it just says about digital data generally, I get the feeling that they tend to write those questions with sound in mind. So how do we turn sound waves into numbers? Because remember, to store something digitally, at the end of the day, they have to be turned into numbers. Well, quite simply, what happens is that the sound is sampled. Now, that's a really important word, sampling. And what sampling is putting the sound wave on a grid again, kind of like a graph. when you measure, when you make a graph in science or in maths, and it's measuring the sound wave. And it's measuring the sound wave in order to try and measure and follow the curve of the sound wave as closely as possible. Because then, when we want to hear that audio back, it'll just build up the blocks, and the blocks will try and match as closely as possible what the original sound wave sounded like and play that back. The closer that we can get to the original curve, the better the sound is going to be, the more accurate it's going to be. But if we want to save space on our device, then maybe we'll use a lower sampling rate and a lower sample resolution, which will then end up cutting the corners of our nice curved sound wave, which curves endlessly because it's analog. But if we record it, sample it with a low sample rate, as you can see on the left-hand side there, you're going to cut corners. And when it plays it back then, it's going to play it back with those jagged edges. And I'm sure you've all been on a Zoom call or on a FaceTime call or even on a phone call where suddenly your network loses speed. Your connection speed decreases. And all of a sudden, the person's voice that you're listening to starts to sound a little bit robotic. Yeah, you start getting a bit glitchy, maybe you'd call it, a bit laggy. And that's what that is. When it lags, it's lowering the sample rate. And what you're hearing are those cut corners of the sound wave, which sound a bit weird. Okay, so why then would you use a low sampling rate? Well, of course, it's the same as with the pixels we were talking about with images earlier. A higher sampling rate, the one on the right-hand side, as you can see, it follows the curve much closer. But that's going to use way more of your storage because you've got two levers. You can sample more often. You can sample more, which is called the sampling frequency. Okay, so I'm sure you're used to that word. It's a sample frequency. So the standard sampling frequency for audio is 44.1 kilohertz, which means it is going to measure the sound wave just over 44,000 times per second. That's a lot of measurements, right? But if you wanted even better sound, you could turn that up. Okay, the next step up is 48,000 something times a second. And you can step it up again. So obviously the more often you measure the sound wave, the closer it's going to follow the curve of that sound wave. But the more often you measure it, obviously, the more of your memory you're filling up with those measurements. Now also, you can vary the sample resolution. It's also known as the bit depth. And that is how many bits of your storage you're going to actually allocate for each sample. So if we were talking about the normal sample frequency, which is 44,000 times a second, so every 44,000th of a second, how many bits of data, how many little switches in our storage do we want to use? So obviously the more bits that you use, so the deeper your bit depth, the greater your sampling resolution, then the closer again we can get to the curve of our original sound wave. But on the left-hand side, you can see that the sample resolution is quite coarse. So you can see there, because the blocks are so big, that it really has to cut corners, and it isn't really representing that curved sound wave very well at all. Remember, when these are turned back into sound for us to hear, well, the original sound wave isn't there. The original sound wave was analog, and that's gone. So the computer or your device will build up a sound wave, something similar to a sound wave, from the numbers that have been stored digitally. So what you'll get played back is, if you look on the bottom image there, it's the right-hand side, you'll hear back that kind of staircase representation of the sound wave. Okay, and the closer it is to the original curve, the better and more accurate it's going to sound. Okay, so that's sampling. So how does it work then? How do we go from analog to digital and then maybe back to analog? Because if you're listening to me right now on a digital device, but you're living in the real world, which is analog. So the sound waves that are coming to your ears right now, whether it's through your speakers or through headphones, or if you've got earphones in or whatever, those sound waves that are coming into your ears right now are analog. Okay? But between my voice being analog right now as I'm speaking and it getting to you, where you can hear it, which is also analog, it's been converted to digital because I'm speaking, my microphone is connected to the computer, which is a digital device. So it has to be converted to digital, but then it has to be converted back from digital to analog in order for you to actually be able to hear it. So let's talk about that process. That process is called conversion. And we got a little simple flow chart here, okay? So to convert from analog to digital and digital to analog, you need to have little computer chips, which are called little circuits, which are called converters. And you need two different converters. You need an AD converter, analog digital converter, which is going to convert your analog sound, in this case, data, into digital data. So you can store it on a computer or send it over the internet like we're doing right now. But then at the other side, so in our little example here, on your device right now, you need a digital to analog converter, which is going to take all the ones and zeros that my computer has put together for my voice right now and turn it back into something resembling a sound wave, as close as hopefully possible. Okay, so you can see there, there's a microphone there. Now, some microphones are totally analog. The microphones that you've probably got in your school hall that have got quite a thick cable plugged right in the bottom of it, goes straight into a mixer or straight into an amplifier, which comes out of the speakers in the hall, that's going to be a totally analog setup. Okay, it's not being converted, it's analog all the way. And that's why you maybe hear static and interference coming over those. But this microphone I'm using here, okay, this is a USB microphone. There's a USB cable here that's plugged straight into my computer. So how does this work? Well, the front end of this works exactly the same as a normal microphone, a normal analog microphone. It's measuring the sound waves that my mouth is producing using magnets, really, okay, and it's turning it into kind of magnetic symbol, electrical signal. Now, at the bottom of my microphone, at the bottom here, there is an AD converter, a little computer chip, a little circuit, which right now is sampling my analog voice sound waves, measuring it, and sending that then, those numbers, down my digital USB cable to my computer. Okay, so my voice is analog here. By the time it leaves the microphone, it's already digital. So then obviously it's traveling over the internet. It's stored on my computer, it's traveling over the internet. And that's all digital. Has to be, doesn't it? So that's all ones and zeros. So what happens then at the other end? So right now, if you're hearing my voice, your device has received the digital information, the digital data of my voice right now. And you've got a DA converter, a digital to analog converter. Now, this is usually going to be really close to whatever's making the noise. Okay, so if you're listening through your speakers, then the DA converter is going to be in the sound card of your device, which is next to the speakers usually. Okay, the sound card is going to be close to the speakers and close to where maybe you can plug headphones in, like a headphone port. If you're listening on Bluetooth earphones, like AirPods, well, your device, or maybe your phone or whatever device you're watching me on, is sending the digital data through Bluetooth, which is a wireless digital connection, to the earpods. So it gets to the earpods, to your wireless earphones, digitally, and then in your wireless earphones, That's where the DA converter is. Okay? So your device is throwing ones and zeros up in the air like this at your wireless earphones, throwing them out there, and your wireless earphones going, oh my goodness, and collecting it all up. And then in your wireless earphones, there's a little chip which is basically building that sound wave as close as possible, but it's going to have the kind of staircase thing that we saw in that last slide, and then throwing that out throwing that analog sound out from the tiny little speakers which are in your wireless headphones into your ears. Okay? Because, like I said at the beginning, we live in the real world, and the real world is analog. Okay? I can't send you a load of ones and zeros and you hear it. You can't hear ones and zeros. They have to represent something. Those numbers that are stored have to be built back together into something that as close as possible to a sound wave. All right. What's next? Question. Describe the steps of converting an analog signal to digital data. 3 marks. So you need to give me 3 good points here, otherwise you're not getting 3 marks. You will not get 3 marks for making 1 point. You will not get 3 marks for making 2 points. You will only get 3 marks if you make 3 points. And if you want to be safe, make 4 points. Because if one of your points is bad, then you can still get full marks because you'll make 3 good points. Okay? It's given you 1, 2, 3, 4, 5, 6 lines here. Now, you do not need to fill all 6 lines, but it does suggest to you that a kind of 4-word sentence is not going to cut it to get full marks here. Otherwise, why would they give you 6 lines, right? You know that though, right? Right? So, what are the steps of converting an analog signal to digital data? Now, bear in mind, does it say there, does it ask you about converting it back to analog so you can hear it? No. Okay? So don't fall into the trap of describing steps that it hasn't asked for. It's just asking you to describe the steps of converting an analog signal to digital data. So the end of this answer is going to be storing digital data. Okay? So that's the last mark you'll get of your 3, is that the data is stored digitally as ones and zeros. Okay, that's kind of the last thing. You don't need to say anything after that. Okay, so let's talk about converting it. Well, how are we going to get those other 2 marks? Well, you need to use the word sampling. Okay, so you could talk again. Now, do you notice here it doesn't say sound in the question? That's what I was telling you earlier. If you see a question like this and you're like, oh man, I'm not sure what they want me to say here. If it's talking about analog and digital and it's not obvious, think about sound. Okay, think about sound. And that's usually the context that they want you to answer in. Okay, so what happens then? Well, the analog sound wave is sampled, where the sound wave is measured many times a second. Okay, those measurements then are stored as numbers, which are converted into binary, which is ones and zeros, which are stored digitally on your device. Okay, and that's it. That's all you got to do there to talk about that. You could also throw in there about an AD converter. That would be good. That would be a great little mark, wouldn't it? Yeah, an AD converter does this. That's what we call the little electrical circuit that does this, that does the sampling. It's an AD converter. So I've made 4, maybe 5 points there. So I'm definitely getting those 3 marks. Yay me! I'm getting 3 marks. Okay, so our final slide then, guys. Okay, bear with me. We're nearly there. Now, analog data, digital data have got advantages and disadvantages. Now, maybe you've been listening to this and you're like, okay, I get it, dude. Analog data is the best and digital data is not great because analog data's got all the information and digital data doesn't, because it samples and at some point you hit a brick wall. Now, it's not as simple as that, I'm afraid. Okay, because I grew up in the 80s and the 90s, and I used to watch movies on VHS tapes, videotapes, big black plastic boxes that you'd put into a video player. Okay, now that is analog. and the video quality on a VHS was bad. Now, why was it bad? It wasn't bad because it's analog. It was bad because the analog devices that played it and recorded it originally introduced a lot of static and interference into what was recorded. So it didn't look great. I could zoom in on it forever if you kind of wanted to. You could zoom in on it forever and you'd never hit a brick wall where you'd kind of, oh, it's just one big pixel now. But that doesn't mean that it was great. Okay? It just means that all the data was stored. Some of that data was static, interference, noise. Okay? But the advantages of analog data is that because continuous data is stored, there's no deterioration in the quality of the data, so it is all there. Whether it's all good or not is up for debate, but it is all there. Nothing's been left out. Okay? And I think with audio, listening to music, that's where you'll mostly hear people saying analog is better. People that like listening to LPs, to vinyl, they will bang on at you about the fact that vinyl is better, man, because it's got all of the information and nothing's been cut out. And if you listen to MP3s, it's like, what's the point? So, vinyl snobs have got a point, because vinyl LPs, records, do have way more data and more sound information than their digital counterparts. But what's the downsides then? What's the disadvantages of analog data? Well, analog data, records, dust gets in those grooves. They can scratch. The plastic, if it's sitting next to a window and it's sunny, those plastic discs can actually warp. Okay? And then, as I was saying there, at the end there, you can get signal corruption when recording. So when you're using analog equipment, it's far more prone to having kind of signal problems, noisy signals, interference, static, kind of white noise, all those kind of things. Grain on a photograph or on a video. So that's a disadvantage. Now then, digital data. Advantages of digital data. Well, you can store way more stuff digitally than you can using analog forms. Okay, a big plastic disc, a vinyl record will hold about 20 songs if you've got flip it both sides. That same amount of plastic as a memory stick or as a chip on your phone is going to hold tens of thousands of songs. Well, that amount of plastic, I mean, you wouldn't fit it in your phone, would you? The same amount of plastic that's on an LP would hold millions and millions of songs. Millions and millions of songs, okay? So we can store way more data in a much smaller space if we store it digitally. So that's a big advantage, right? Disadvantages of data, of digital data. Well, I think we've spoken a lot about this during this session. And really it's that anything digital has to be sampled. You have to decide how you're going to break that down into a grid so that you can turn that grid into numbers so you can store it in your bits as ones and zeros. By making that decision, by sampling, you are deciding on how much information you're willing to lose from the original analog data. And that's a major disadvantage. Even if you wanted to say, I don't lose any data. I don't want to lose any data at all. I'm going to record sound and I'm going to have a massive bit depth. I'm going to use, 100 bits per sample, and 44,000 times a second isn't enough for me. I want to sample 100,000 times per second. Okay, you could do that, and you would have gigantic file sizes, and you'd have loads of information. But if you wanted to zoom in on one tiny fraction of a second of that sound, at some point, you're going to see big, jagged staircase edges, not a nice curved sound wave. It doesn't matter how much detail you want. At some point with digital data, you have lost information. Okay? All right. That's been a lot of fun. I hope you've made it to the end. And I hope you make it to the next session where we'll be looking at 1.2, storing data digitally. Oh, easy for me to say. And hopefully you can come to the live session. Please come to the live session, even if it's just to say hello, okay? Don't need to ask a question, but questions are great as well. Don't ask me anything too hard, okay? That's really embarrassing in a live session. So, all right. So thanks again for watching, and I hope I'll see you again on another session before long. Okay, bye for now.